In this video, we solve problem 8.R.061 from the Larson and Edwards Calculus Early Transcendental Functions texts, 7th edition. We're asked to evaluate the integral, the indefinite integral, using any method, and we have this right here. Now, on the surface, the first thing I always ask myself is, do I have a basic rule for that? And we don't. We've got the square root of this function. But since I have a function nested inside another function, my next instinct would be to try u-substitution. So I would say, let's let u be the function inside, that's 1 plus cosine of x, and then I would compute the derivative of that. But the derivative of 1 plus cosine of x is this. The derivative of 1 is 0, and of course the derivative of cosine of x is negative sine of x. So du is that derivative times dx. So I would try u-substitution because I've got this function nested inside another function, but if I don't have this cosine of x dx factor up here somewhere, this isn't going to work. I can't write everything here entirely in terms of u without any x's at all, because du involves a sine function, and there is no sine function up here. So that's when I would go to the 9 common techniques that we've talked about in our course, and I would recall to myself that if I see a 1 plus cosine, or a 1 minus cosine, or a cosine plus 1, or a cosine minus 1, or something that looks similar to that, but with sine of x instead of cosine of x, or sine or cosine of kx, if I see that form, the guideline says you might try multiplying by the conjugate. So that's what we're going to do. And it turns out that multiplying by the conjugate will work for us. Now, just as a reminder, the Pythagorean conjugate of a plus b is a minus b, and the Pythagorean conjugate of a minus b is a plus b. And when you multiply these two together, you multiply two conjugates together, first times first always gives you a squared, outer times outer is negative ab, and inner times inner is positive ab, so those middle terms cancel. And then last times last is b times negative b, which is negative b squared. So we're going to multiply by the conjugate of 1 plus cosine of x, and then we're going to simplify using the fact that this times this is this difference of squares over here. Okay. And again, the reason that I know to multiply by the conjugate is because of those guidelines that I mentioned earlier. If you have a 1 plus cosine, 1 minus cosine, or something that looks similar involving sine of x instead, and of course the 1 could be last instead of first, that would be fine as well. You could do cosine plus 1 or cosine minus 1. For all of those problems, we multiply by the conjugate. Anytime I see something that looks like that involving sine or cosine, or like a sine or cosine pair, or a tangent or secant pair, or a cosecant and cotangent pair, or one of those, plus or minus 1 on either side, then I think about multiplying by the conjugate. So we're going to multiply by the conjugate here. The conjugate of 1 plus cosine of x is 1 minus cosine of x. But I can't just multiply by 1 minus cosine of x because I have this square root. So if I want everything to work well, I need to multiply by the square root of 1 minus cosine of x. And then I can't just multiply by that because that would change my entire integrand. So I need to multiply by this conjugate over itself, because that's just multiplying by a well-chosen 1, and that's not going to change the value of our integrand at all. And of course, there's an implied 1 right here. And we might think of that integral sign as much bigger now. Okay, so we have this. I have the square root of 1 plus cosine times the square root of 1 minus cosine. And then we have this fact. The square root of a times the square root of b is the square root of a times b. So you just write these under 1 square root and multiply them. And when I multiply 1 plus cosine of x times 1 minus cosine of x, according to this, I'm going to get 1 minus cosine squared x. Or if you prefer, you can just FOIL. First times first is 1. Outer times outer is negative cosine of x, and inner times inner is positive cosine of x. Those reduce, and then last times last is negative cosine squared x. And then we just have 1 times this in the denominator, and so it's still there. Okay, so I told you that guideline, that it was related to those, the sine cosine pairing, or the tangent secant pairing, or the cosecant cotangent pairing that we see in our Pythagorean identities. And I think that when you simplify this, now you can see why. This 1 minus cosine squared simplifies because we have a Pythagorean identity involving sine and cosine. Remember this identity: sine squared of some angle plus cosine squared of the same angle is equal to 1. So if I subtract cosine squared from both sides, I get sine squared A is equal to 1 minus cosine squared A. That's pretty nice. So 1 minus cosine squared under a radical that 1 minus cosine squared of x here can be replaced by sine squared of x according to that identity. Now, generally, the square root of something squared is not exactly that something, but if the expression under the radical is positive, the squaring function and the square root function undo each other, and you just get x back. So let me write this fact down for you. The square root of x squared in general is just x, but that only works if x is strictly greater than or equal to 0. Now, we don't have any domain restrictions here, so I think I'm just going to call that sine of x. The square root of sine squared x is just sine of x. But in order for those to truly be equal, this is assuming that sine of x is greater than 0. If sine of x is less than 0, then we actually have to multiply by negative 1. I'm not going to get into that too much right now. But yeah, this is equal to this, provided that x is actually non-negative. All right, so now we're here, and then we look at this, and we look at it as if it's an entirely new problem. Here we need to multiply by the conjugate. We always distribute the conjugates and simplify, often using our Pythagorean identities. And now we're here and we say, okay, do I have a rule for that? No, we don't have a rule for that. If we don't have a rule for that, the next thing we ask ourselves is, will u-substitution work? And it turns out that u-substitution works this time. Now remember, with u-substitution, you're looking for a function nested inside another function. A 1 minus cosine of x is inside that square root. So that's a good choice for you. And we're never 100% sure that u-substitution will work until we compute du, and we know that we can rewrite everything up here entirely in terms of u. The derivative of 1 is 0. And bring the negative down. The derivative of cosine of x is negative sine of x. So negative sine of x. It's going to be positive sine of x. And du is that derivative times dx. So we say, do we have a sine of x dx up here? Well, we sure do. It's right there. Okay, so now we can write everything in terms of u. Sine of x dx is du, according to this line. And then I've got a u, but careful, it's not just a u. It's a square root of u. And it's not just a square root of u, it's in the denominator. So that's what we have as our integrand. So then we say to ourselves, do I have a rule for that? We say, kind of, not yet. But if we do a little bit of algebraic manipulation, we can rewrite this in such a way that we do have a rule for that. We can just rewrite this as u to some power and then use the power rule. The two things that we need to remember for that are that the nth root of x to the m is x to the m over n. And with a square root, there's an implied 1 there and an implied 2 there. So this is a u to the 1/2 power, according to this rule. Another rule that we need to remember is that 1 over x to the n is x to the negative n. So you can bring this up to the numerator as long as you change that exponent from negative or from positive to negative or from whatever sign it is. You just flip the sign and then it's going to go up there. So that means that this is actually u to the 1/2 power, but since it's in the denominator, when I bring it up to the numerator, it's going to be negative 1/2 power. And now I can just apply my power rule. So we will add 1 to the exponent, and then divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2. You can think of it as 2 over 1 if you want, but then you sort of ignore the 1. And then don't forget to add your constant of integration. And then lastly, remember you're not done yet until you write everything in terms of the original variable. U is just something that we made up so that we could apply these rules and compute the antiderivative. I need to go back to x. So I have to remember, oh, well, what was u in terms of x? U is actually 1 minus cosine of x. And I can make that substitution here. And again, the square, or the 1/2 power is the same as the square root. So I would write it like this. So this is 2 times 1 minus cosine of x, or the square root of 1 minus cosine of x, plus c. Okay, so I just want to go over one more time what we did, the outline of this method so that you know how to handle it. You look at the integral, you ask yourself, do I have a rule for that? You say no. Say it's u-substitution appropriate, You might say maybe, and then you might see, oh, there's no sign of x, so it doesn't work out. So u-substitution can't apply as it's written. So we say, oh, there's a 1 plus cosine. Let's multiply by the conjugate. So we applied that technique here. And make sure that you're multiplying and dividing by the conjugate so that you're actually multiplying by a well-chosen 1. So then we distribute and simplify. And we're using that Pythagorean identity here. And we're often doing that when we multiply by the conjugate. And then we look at this as an entirely new problem, and we see this time after the rewrite, u-substitution is appropriate. So we'll say, let's do u-substitution. So we're going to choose u to be the inside function, compute du. You write the integral in terms of u. And you want it entirely in terms of u. There shouldn't be mixed variables here. U's only or x's only. And simplify so that your basic rules apply. And then the next thing we did is we anti-differentiated using that basic rule, our power rule, and then we back substitute. Don't forget to replace u with whatever it was in terms of x. In this case, we were replacing u with 1 minus cosine of x because that's what u was when we initially decided on our substitution.